Dear friends, in the sequence of the phylum Mollusca, of which we have discussed two classes, class Lamellibranchia and class Gastropoda. In this lecture, we will be talking about the class Cephalopoda. The class cephalopods, they are the most successful mollusks and they have a well developed nervous system, but being paleontologists, we have only hard parts before us. So, we will be dealing with only those forms which are fossilized. Some of those forms have recent counterparts as well. The cephalopods bear the common characteristics of the phylum Mollusca as having the calcareous shell. Then the cephalopods have been divided into three different parts. One is Nautiloidea, second is Ammonoidea, and the third is Dibranchia. Nautiloids, basically this word has been derived from nautilus. So, this Nautiloidea, order Nautiloidea, it bears few characters. The first characteristic feature of this order Nautiloidea is that it has a straight suture or the slightly curved suture. As you can see, these lines which are visible when you observe this very carefully. So, these lines are slightly curved, whereas here they are straight. So, they have simple suture, simple, straight or slightly curved. Then we have Ammonoidea. Ammonoids, they have the complicated suture lines. As you can see here, the suture line is little complicated. We will be discussing this in the foregoing session of this lecture. And then third is the Dibranchia. Dibranchia, they are those forms whose skeleton is internal. All the nautiloids, all the ammonoids, they have the external skeleton, whereas the Dibranchia, they have the internal skeleton. So, this one is an internal shell and it is not coiled. We will discuss the morphological details a bit after. The fossil counterpart of the Dibranchia is Belemnitis. In the recent or the modern world, the resemblance to the Belemnitis is found in octopuses. You may have seen octopuses. So, the octopus resembles the Belemnitis and it belongs to the Dibranchia order. Let us start with the morphological features that is to be observed by a paleontologist while describing the cephalopods. The first is the shape and size of the shell. As you can see, this nautilus, this is rather of the large size, whereas this one is an ammonoid which is called as Hoplitis. This is relatively smaller, whereas in between you have this Ceratitis, it is a fossilized ammonoid of Triassic. This can be, and this Hildoceras, this can be said to be of the medium size. So, you have the larger size, intermediate size or the smaller size, and then comes the shape of the shell. After size comes the shape of the shell. The shape of this shell, you can say that this is little globular in shape, this is orthoconical form, this one is laterally compressed. Here also you can see the shell that is laterally compressed. This is also discoidal and it is compressed also in the middle. This is called as biumbilicate form, whereas some of them they have the raised central portion they are called as biembonate forms. So, you can, this one is guard like. So, you can have different shapes and sizes of the cephalopods. After the form of the shell, we will be describing the coiling. The coiling of the shell, sometimes it is planispiral and sometimes it is even not coiled. Here you can see all the chambers, these are different chambers. So, these chambers are arranged one over the other. So, this is straight line growth of the shell and there is no coiling. So, this particular shell will be called as uncoiled, whereas here the successive chambers have been added and the shell takes a coiled form. So, this one will be coiled. Now, in the coiling also there are two different types actually. The first type, in which the later whorls will not embrace or cover the earlier ones. This is called as evolute coiling. But at some places you can find that the later coiling, it covers or embraces the earlier ones, and this is what we call as involute. Like for example, if you see this nautilus, if you extend this particular sense of coiling in this direction, you will observe that this particular earlier whorl would be covered by the subsequent growth of the shell. That means this particular form, if you see right through the axis of this coiling, it is involute, that means it covers the earlier portions, earlier whorls. Whereas on the other hand, if you see this particular sense of coiling, in which you can see the earlier whorls also and the later whorls as well. That means the later whorls, they do not cover the earlier whorls. This particular coiling is called as evolute, whereas this one which covers the earlier portions is called as involute. But these are not the two only end members found. There are some cases which are exactly in between these two extremities, and this is which is called as partially evolute or partially involute. Here the earlier portion is covered only partly it is visible, partly it is invisible. So, you can have partially evolute or partially involute forms. After this the coiling, we will be discussing about the shape of the aperture. Here the aperture is oval, here the aperture is exactly circular or rounded. Here the aperture is crescent shape or semilunar. Here the aperture is oval. That means the shape of the aperture is also a feature to be observed by a paleontologist or a geologist. Now, we will talk about the siphuncle. What is siphuncle? Let me tell you about the siphuncle first. That means, let me tell you that as you can see that this is a suture line between these two chambers. These are basically chambers in which the animal lived. So, when the animal grows, this particular chamber becomes unfit. So, it forms another chamber and shifts into that. But if during the growth of that organism, if that also becomes a small, it makes another bigger chamber. So, the chamber becomes bigger as per the size of the animal, and it shifts from one chamber to the other. So, the passage from one chamber to the other is a kind of an opening, and this opening is called as the siphuncle. Here this opening is shown by this particular circular feature. So, that means if you add another chamber here, through this particular opening the animal can shift from one chamber to the other. So, that means each successive chamber will have the siphuncle. You see, in the first chamber also you have a siphuncle. So, one siphuncle is here, the other is here. So, if you join the two, you will get a straight line. That means here the siphuncle is not curved, but when the forms are curved, when the shell is curved, the siphuncle also becomes curved, as you can see here. This is one chamber, this is septa, this is another septa, and you can see the siphuncle running. So, if the shell is curved, the siphuncle will also be curved. So, the forms which are basically nautiloids, as I told you, with the simple suture, the siphuncle, the pattern that the siphuncle curvature makes is called as retrosiphonate, whereas in the ammonoids, which have the complicated suture, external shell and complicated suture. So, here we have the siphuncle pattern as prosiphonate. Then comes the suture. Suture is a very important feature in studying the cephalopods. As far as the suture is concerned, it is subject matter of only the external shells. The cephalopods having only the internal shell, you do not have any suture. That means suture will be studied only in the cephalopods with an external shell. So, that means these shells which I show you only will have suture. So, suture can be simple and straight, like here. You see, this suture is simple and straight in Orthoceras. The suture can be slightly curved, as in case of Nautilus. As you see from this axis of coiling, that is umbilicus, the sutures emerge and diverge in a pattern which is a curvilinear or the straight, simple, slightly curved. But if you see the suture lines in ammonoids, the suture line is present in all the ammonoids, but in this particular form, that is baculitis, I will be able to show exactly how they look like. See, you can see here, these are the auxiliary lobes, whereas if you see the sutures here, you will be seeing only lobes and saddle. That means suture is curved, that is, this one is ceratitis, but this is simply curved with one convex and concave form, and they alternate with each other. So, this is called a saddle and lobe pattern. So, this particular suture is called a ceratitic suture, that is characteristic feature of the genus Ceratitis. The next aspect about the cephalopod to be studied is suture. Suture lines are very important part of the cephalopods. What are suture lines? Suture lines are the lines, actually, as I told you, these are all chambered forms, whether coiled or uncoiled, they have chambers. So, each chamber is like a room. So, you have walls between two rooms, as you may have seen. So, that wall between the adjacent room is called as a septa. But when you see this expression of that wall from the roof, that will be the kind of a line, and the nature of the line will reflect the nature of the wall also. So, that surface manifestation of the septa is a suture. That means the form and geometry of the suture reveals much about the identification of the cephalopods. Like as I told you, here the suture is simple and straight with quadrangular chambers, rectangular chambers, simple and straight sutures, and this form also is uncoiled. In coiled forms like Nautilus, you can also see this is chamber, this is septa, and since this is slightly curved septa, because of which we have the slightly curved suture line also. In some forms like ammonoids, the suture pattern little bit complicates from simple slightly curved to little more curved, as you may be seeing here. The suture is characterized by saddles and lobes. That means these are undulatory. So, these undulations are called as saddles and lobes. That means in ceratitis, this particular suture pattern little bit more complicates, and this is what we call as the ceratitic suture. Then the further complexity of this ceratitis, that means the saddles and lobes, they get even much more branches onto them, and this can complicate as complicated as like this. You can see the saddles and lobes both have even auxiliary branches coming out. That means the suture pattern still complicates. Now, the question comes, why at all the cephalopods had to complicate their sutures? The answer to this question is that a particular suture which is simple and straight will have less area. But if you create folds and the undulations, you will increase the surface area. So, when you can think of a shell that is suspended in the water column, so it exhibits the load of the water column. That means, if it wants to go to the depth in the water column, that will be substantiated by even increase in the hydrostatic pressure, and this may lead to the collapse of the shell. That means the shell has to withstand that hydrostatic pressure. So, force is something which the organism or the animal cannot reduce. As you know that pressure equals to force upon area. That means you cannot reduce force, but if you increase the area, the pressure will be reduced. And how this organism can increase the area? By complicating the suture. The more complicated the suture becomes, the more area it covers and the less pressure it will be suffering. So, it can go to deeper or at different and independent levels that it may like to. But what is the need to go to those different levels? They need to get more food. That means organisms, the basic fundamental biological principle is to stay alive. That means every organism tries to maintain its safety and tries to search for food. So, in search for food, they have complicated their suture, and they have gone to several ecological niches. So, they become very widely spread horizontally, but their body was not at all intended or organized by the nature to live in every ecological niche. We can live in very small range of temperature and pressure. If you increase the temperature from our threshold range, it will be very difficult for any being to survive. So, if I, for example, if I land in this shirt to Antarctica, the moment I land, I will die. Why? Because my body in this shirt is not acquainted to live in the minus 40 degrees Celsius temperature. That means, if you increase the horizontal extent of a particular organism, its vertical extent, that is the time by which it survives on the earth's surface, will be reduced substantially. So, this is one of the reasons why the ammonoids with that much of a complicated suture became extinct at the end of the Cretaceous. And then comes the other, after this suture comes the ornamentation. As far as the ornamentation is concerned, you can see you have the tubercles or spines in the Hoplites. This is a very peculiar feature. Then you may have the forms with very low costae. This is one ornamentation. You can have an ornamentation which leads to the ribs, radial ribs, and sometimes these ribs can be bifurcating. Here you can see the bifurcating ribs. So, this is one feature, and then sometimes you can have the ribs in which some ribs are not bifurcating, others are bifurcating, so they alternate with each other. Then comes the organisms in the cephalopoda with internal shell, and the best example is the belemnitis. So, this happens to be an internal shell over which the soft body parts, they tends to balance themselves. And as you can see here, the outline is circular, it is a guard shaped shell, internal shell, and when you cut it, it's little broken, so I am holding this end to end. So, as you can see that this is a triangular cavity, this is called as phragmocone, and siphuncle runs all through. So, you have the siphuncle that leads to the phragmocone, and then you have the radially arranged crystallites. The central axis is a little eccentric, this is called as alveolus, and from this alveolus the crystallites, they radiate in every direction. And there is another plate which is called as prostracum, which is present over this guard or the phragmocone, but it is very rarely preserved in the fossil record. So, this is the belemnitis guard, which characterizes the third part of the cephalopod out of the Nautiloidea, Ammonoidea. This one is the dibranchia with the internal skeleton. Ammonoids, they are very successfully used for the Mesozoic biostratigraphy. They provide very excellent time control in the stratigraphy, and all of them, mostly all of them, they are very good index fossils. Why? What is an index fossil? Index fossils are those fossils which have a very short vertical range and a very wide horizontal range. Short vertical range means they appeared and disappeared on the earth for a very short time, but they were present everywhere on the surface of the earth. That means they have a wide horizontal range and a very short vertical range. What is the connection between the short vertical range and wide horizontal range? That is very natural, as I told you, that if an organism prefers and modifies its shell, as I told you, by complication of the suture lines, to such an extent that it is found everywhere on the earth's surface, naturally the form and architecture of the body, the biological architecture, doesn't allows any organism to live everywhere. A particular organism is an expression of the environment in which that organism lives. That is a kind of an equilibrium between the organism and its surrounding. So, you can remain healthy and safe as long as you are in equilibrium with your surrounding. The moment you try to go everywhere and live everywhere, your time range will be shortened. This is why the ammonoids, they had a very wide horizontal range, but a very short vertical range, and because of which they were very successful index fossils. As far as the geological age is concerned, the Nautilus ranges in age from Triassic to recent. Orthoceras, which is also an nautiloid, it ranges from Ordovician to recent. As far as the ammonoids are concerned, this is Perisphinctis, the age is Jurassic, upper to lower Jurassic, rather mid Jurassic. Hoplites ranges in age from Jurassic to Cretaceous. This is Hildoceras, this is lower Jurassic form. This is Ceratitis, this is a Triassic form. This one is Perisphinctis, this is upper Jurassic. Let me tell you about the Perisphinctis. These are the two same Perisphinctis fossils, but they are of different kinds. This is the body fossil. That means this is a calcareous shell which is preserved little altered, but this one is a kind of an impression over the sediment surface. So, this is a kind of an external mold. Anyway, the age is Jurassic. Then coming to the dibranchia, the dibranchs are represented in fossils as belemnitis. The age is Jurassic to Upper Cretaceous. Then comes the baculitis, that is Upper Cretaceous. Baculitis is a J-shaped form. Actually, this is little broken. So, baculitis is straight, then the early portion is curved and the later portion becomes straight, just like the English letter J. The early portion is coiled and the later portion becomes uncoiled. Baculitis happens to be the Upper Cretaceous form. Hence, we have seen the special characters of the cephalopods, and that is referable to the nautiloids, ammonoids and dibranchs. And there are, every cephalopod is characterized by some very peculiar features. Suture, as I told you, is the most important thing to be noticed. And actually these fossils, they teach us a lesson that, as you can see, the nautiloids, they appear earlier and they are even found now with a simple and slightly curved suture. But those that appeared and became very successful with the complicated sutures, they became extinct for no time to come. That means, if you adopt a simple life, it will be easier for people to survive more than those that adopt a complicated life. With this, I conclude my discussion and this lecture on the morphology of cephalopods. We will be discussing about more of the paleontological groups in the lectures to come. Till then, thank you so much.